we're going to go into a more challenging tree problem. And this one is going to be called path counter, okay? And what the path counter is going to do is going to return the number of paths in the tree T that have a sum larger than or equal to n, okay? And it says that we should use the one function to our advantage. So the one function basically returns 1 if whatever we pass in is a true value, and 0 is a false value. So what the one function essentially does is it basically translates true and false to 1 and 0 respectively. So that's how we can think of that. Okay, so let's look at this example and see how this works. So the best way to do this is to just honestly go through the diagram of the tree, because that's the only way it makes sense to me at least. So if we have path counter on this tree with n of 3, so remember what we want. We want to return the number of paths in T that have a sum larger than or equal to 2. So what does it mean for something to be a path? Well, let me denote what the path means basically. So let me get the pen. And so here, a path is basically something from the root to a leaf, okay? So I think the best way to demonstrate is by going with denoting it in this tree. So one path we have is this right here. Another path we have, so let me go with a different color. Actually, no, that's not different. Another path we have is from here to here to here to here, okay? And another path that we have is from here to here to here. So we have 3 paths in this. Now, what does this function want? It wants to return the number of paths in T that have a sum larger than or equal to n. So let's look at the red path. That's 1 plus 2. Is that larger than or equal to 3? Yes, so that's counted. Then 1 plus 3 plus 4, is that larger than or equal to 3? Yes, and so obviously 1 plus 3 plus 5 is also going to count. So in this case, when our limit is 3, we get all 3 paths included. Now what if our limit is 6? Well then the 1 plus 2 path is not counted because it's not greater than or equal to the n. Okay? And then in the case where we have 9, only the blue path is included because that equals 9, whereas 1 plus 3 plus 4 is equal to 8. So not good enough. So that's the basic idea of the problem we want to solve. So how do we go about solving this problem? So the way I'm going to go about solving this problem is really look at simpler cases of the problem. So again, let's go into our doodle page that's been very handy for us. So what if I just had a one element tree? So something like this. How would I know whether to count this path? So this obviously counts as a path because it's directly to a leaf. So what will need to happen is it only works if path counter is called with an argument of 2. Need argument of at least 2, basically. At least n has to be less than or equal to 2. So what that means is we basically have a direct definition of when we count the path or not. So our t.entry has to be greater than or equal to n. So what I did, I just flipped it around. This is our t.entry. So t.entry is greater than or equal to n. So if t.entry is greater than or equal to n, we count the path. If not, we don't count the path. What does it mean to count the path? Well, we basically enumerate it as 1. And if it's not true, we get 0. Is there a function that does that for us? Hey, that's where we can use 1. So notice how I'm directly going from one logical idea to another. So if it's the case that my tree is a leaf, so this is the simplest case of this problem. If my tree is a leaf, then I just have to return 1 on whether the t.entry is greater than or equal to n. Okay, that's great. So now let's think of the example where it's a little more complicated. So for this, I'm going to use a different color. What's a good color? Let's do purple. Okay. So now I'm going to make my tree slightly more complicated by having the falling branches. Let's say I have 1, 2, 3. Okay. So what if I call path counter on this? So this is our t now. Oh crap, what did I do? Okay, this is our t, and this is going to equal So what if I put n as 4? Well, then this would give us 2 paths, right? Because we have 1 to 2 and then 1 to 3. And both of them happen to... Actually, wait, no, we would only have 1 path. Sorry, what am I saying? This would be 1 path because only 1 plus 3 would count. It has to be greater than or equal to n. Okay, so how do we go about solving this problem? Well, I'm first going to start at the t dot entry, so my entry is 1, okay? And then I'm going to go into the branch. So how do I know that 2 is not good enough? Well, that's because 1 plus 2 is less than 4, okay? So what I want to find is I want to find the 1 plus some subtree dot entry such that it's greater than or equal to my n, okay? Because in this case, so that we just looked at this case, but now if in this case 1 plus 3, by this case, sorry, this case I mean this case right here, 1 plus 3 ends up greater than or equal to being 4. So this is counted. So what we can cast this problem as is we can realize that at the end of the day, this is our t dot entry. We just need every subtree dot entry to be greater than or equal to n minus t dot entry. So the key idea here is to realize that summing up a path is the same as subtracting as we go down on the path. So we just need to subtract from n each time in our recursive calls, because then that's going to be a simpler version of the problem. Because now, think about this now. If I had only this tree, and I had my 1 already, the path count is just going to have to be return true on my subtree for my n being 3 now, because I've already encountered a 1, so I just need a 3 for it to be true. And this ends up being n minus t dot entry. So this is the hard intuitive leap to make in this problem. But the key idea is if you want to add up the path, you can basically take whatever you want to get and subtract from it until you get to a value that's good enough. So let's implement that logic. So what we want to do is we want to basically return all the paths of a tree. Okay, so what does it mean to get all the paths? Well, we can basically sum over the path counter. So this will count up every path in the subtree, and then every time we go to a subtree, we have to, of course, subtract the original entry from our n, because we've already counted something. And the way we denote counting is subtracting from n, and then we can go through every subtree in t.branches. And this should return the right answer. So let's test that. And it works. So the key idea, again, this is the hardest intuitive leap to make. If you got everything else but this, that's perfectly fine, because this is a little tricky to see. But it's a clever trick when working with tree problems. You want to basically use your larger problem to solve. You want to use the smaller problems to solve the larger problem. So how can we cast the large problem as a smaller problem? So that's the idea there. Okay, so anyway, what we have now is, so let's go to the next slide. What's on the next slide? I wonder. Oh, hey, it's a summary of the course. Congratulations, you just finished the entire course series on Introduction to Programming Paradigms. So this is, again, the first course I was making in this 2-part course series. And the next course, I'm honestly not sure when I'm going to have time to work on that, but if I have any time, I will, of course, work on it. So be on the lookout for that. But anyway, forget about the next course. You're done. So what did we talk about in this course? So I'm basically going to go a big idea summary of what we did. Well, at the end of the day, we learned how computers do the processes that we take so much for granted. So every computer works with a programming language. So programming languages are ways that users can, or basically developers can instruct the computer, hey, I want you to do this. Because again, computers are so powerful because they can do so many operations that we find inconceivable extremely fast. So one thing we talked about in programming languages is what's the basic ideas of every single programming language you're going to encounter. Well, every programming language at the end of the day is going to have some form of expressions. It's going to have assignment statements. It's going to have control. We're going to have something. We also have programming languages that have functions, higher order functions, iteration, recursion, tree recursion. These are all ways to manipulate functional data and basically take information and manipulate it in ways that we want. But how do we store information now? What if we have a lot of data and we need to have some way to store it? Well, then we can use ideas of data such as lists, tuples, dictionaries, sets, and then of course we can change data by having the concept of mutability. And of course we also talked about the huge idea of object-oriented programming, which is like a sub-language in itself. And this is a new way to basically organize programs so that you can for change later and also representing dynamic ideas. And then we also talked about efficiency and memorization. So these are topics that we are usually hit up on in more advanced courses, but I think that you can basically understand the ideas of that. Then we also briefly talked about iterators and iterables and how to implement those, because that's also an important part of understanding how iteration works with the for loop. And then lastly, we closed with two big topics, linked lists and trees, and introduced the concepts of data structures and how they work. And we also did some processing with linked lists and trees. So anyway, you have done quite a lot, so you should feel quite proud of yourself. And so a natural question might be for those of you who are curious, what's next after this? Well, after this, I'm going to be probably working on data structures and algorithms course, which is the next step in your programming career, basically, I suppose, if you want to make this a career. So generally, after you have this intro course, you go into more deeper level of how these data structures work. There's actually a lot more with linked lists, a lot more with trees. There's actually a lot more with trees. But we basically had just hit the cusp of that topic. And then there are also other crazy data structures like hash tables, balancing trees. What else do we have? We have tries, we have sets, we have disjoint sets. Oh man, it's going to be fun. But basically, I mean, these are all basically clever ways to organize data to make for efficient use. So I think that stuff is really cool. And we're also going to go a little more into algorithms. Today you actually got a taste of an algorithm with the turtle and the hare problem, but we're going to go into even cooler algorithms in that class. So anyway, that's like the next step. And even if you don't want to listen to me anymore, you can always look up this type of stuff online, because data structures and algorithms are there's a lot of information about it online. So feel free to look into that. And I guess the last thing I have to say is basically computer science is really cool because in terms of problem solving, when you solve a math problem, you feel pretty good, but a computer science problem is even better because not only do you get the joy of solving the problem, but you also get the joy of actually creating something new. So like, I remember for me, like one of the first things I found was like, hey, I built this isPrime function that like at the start of 61A, and I was like, wow, I can figure out very quickly whether a large number is prime or not. Not many humans can do that, and I just did that within like 2 weeks of programming. So that was like a moment for me. I was like, wow, this is really amazing, you know? And of course, as you go onward, you realize that that's really not that much compared to some other stuff you can do. So like, I mean, it's really amazing what you can do with computers. And you should feel very excited about this topic because basically it's all around us today. Like, understanding computer science really helps you understand the way the modern world works. And I feel like everyone at the end of the day should know some programming at some point. So anyway, that's really all I have. And I'll see you later in the next course that I hope I'll have time for. I'm kind of running out of time this summer, but we'll see. Anyway, thank you so much for listening, and I really appreciate all of you that listen. And anyway, have fun programming. That's all I have. Thanks.